In this video tutorials, we would learn a very easy way to determine the hybridization of an atom. All we need is in 2 steps. 1. The Lewis dot structure for the compound. 2. The number of electron domain or areas of electrons surrounding an atom. When we say electron domain, we are simply referring to the bond locations, specifically the single bond, the double bond, triple bond, or the lone pairs of electrons around a particular atom. Simply put, we can say electron domain refers to areas of electrons around a particular atom. Interestingly, in counting the number of lone pairs and bond locations around an atom, each bond or lone pair is counted as 1, irrespective of the bond type. So whether we have a single bond, a double bond, or a triple bond, or even a lone pair of electron, we consider it as 1, or is counted as 1. The example presented later in this video will elaborate more on this. Before we start with some examples, let's consider this table containing the number of electron domain against the hybridization. For an electron domain of 1, we have S hybridization. This is mostly for hydrogen atoms, which forms 1 bond only. For an electron domain of 2, we have sp hybridization. And it goes on for 3, 4, 5, all the way to 6. For 6, we have sp3d2 hybridization. Since we are familiar with this table, let's begin with our first example. To determine the hybridization of nitrogen and ammonia, we draw the Lewis dot structure for ammonia, which looks like this. Nitrogen as the central atom with 3 nitrogen to hydrogen single bonds and 1 lone pair of electron. We then count the number of electron domain or areas of electron around nitrogen. Counting, we have 1, 2, 3, and 4. 4 number of electron domain. Let's quickly move to our table. From our table, 4 number of electron domain or areas of electron corresponds to a hybridization of sp3. Hence, nitrogen in ammonia has a hybridization of sp3. We then count the number of electron domain. For our next example, we have PF5. When you are asked to determine the hybridization of, say, phosphorus in PF5, from our rule, we first draw the Lewis dot structure of PF5 and then count the areas of electron or number of electron domain around phosphorus. The Lewis dot structure of PF5 shows phosphorus as the central atom with 5 p to f single bonds. That is 5 fluorine atoms around phosphorus and 3 lone pairs of electrons around each fluorine atom, like this. Now let's count the number of electron domain or areas of electrons around phosphorus. Counting, we have 1, 2, 3, 4, 5. 5 areas of electrons. Let's move to our table and confirm what it corresponds to. From our table, 5 number of electron domain corresponds to sp3d hybridization. Hence, phosphorus has a hybridization of sp3d. Amazing. How about the hybridization for the fluorine atoms? Anyways, for the fluorine atoms, they form the same type of bond with phosphorus. As you can see, they all form single bonds with phosphorus. And also, same number of lone pairs of electrons, 3 for each of them. So the hybridization for one of them is the same for all of them. Let's pick one of the fluorine atoms. We pick this very one. Counting the electron domain, we have 1. Don't forget, the lone pairs are also parts. Counting, we have 2, 3, and 4. From our table, 4 number of electron domains corresponds to a hybridization of sp3. Hence, fluorine in pF5 has a hybridization of sp3. Pretty simple. For our next example, we have this organic compound with 1, 2, 3, 4, 5 different carbon atoms. To determine the hybridization of each carbon atom, we follow the same basic principle. Let's start with one of the carbons. We begin with carbon number 1. Counting the number of electron domain, we have 1, that's the single bond over here, 2 for the double bond. Don't forget, electron domain is independent of the bond type. So, though we have a double bond, it's still considered as 1, our rule. And then the single bond here, 3. So in total, we have 3 electron domain. Let's go to our table. From our table, 3 electron domain corresponds to sp2 hybridization. Hence, carbon 1 has sp2 hybridization. We do same for carbon 2. Counting, we have 1, 2, and also our double bond. It's also counted as 1 from our rule. So we have 3 number of electron domain. Let's get to our table. For 3 electron domain, we have sp2 hybridization. And that's the hybridization for carbon 2. For carbon 3, we have 1, 2, 3, and 4. Referring from our table, 4 number of electron domain corresponds to sp3 hybridization. Hence, carbon 3 is sp3 hybridized. Let's move to carbon 4. For carbon 4, don't be confused with the triple bond in there. Remember our rule that electron domain is independent of the bond type. So the triple bond we have in there will still be counted as 1. So let's start doing the counting. We have 1 and 2 for the triple bond. Referring from our table, an electron domain of 2 corresponds to sp hybridization. Hence, carbon 4 is sp hybridized. Do same for carbon 5. I believe you've learned a lot. Anyways, I have a special bonus for you for watching to the end. Drawing Lewis dot structures at times can be very hectic and time consuming. To save you from all this trouble when determining hybridization of a particular atom in a compound, I deduce a formula called AMI on 2. AMI because the variables in the formula combines to form the word AMI. This formula would save you from the stress in drawing Lewis dot structures. I'll just help you to determine hybridization of atoms easily just by calculation. If you enjoyed the video, like, subscribe, and share for others to benefit.